Hello all, my name is Ashutosh. I am a teacher by profession. My mission is to impart quality education for all. For that purpose I am creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos.
Today we are going to discuss about analysis of quantization error for linear quantization in pulse code modulation system. So these are the outlines. We'll start up with the introduction. Then we will try to define what is quantization noise, or we could say quantization error. Then we are going to evaluate the quantization noise with the help of random variable theory. Then finally we are going to conclude with calculating signal to quantization error in PCM system while we are assuming linear quantization or uniform quantization. So in the last lecture, we have discussed about the quantizer and its various types. We have discussed about the mid-read and mid-rise type of quantizer. We have also understood that since we are not passing the exact signal and we are passing the approximated one, so obviously we are inherently introducing an error, and that error is producing due to the quantization process. That is why that error has been called as our quantization error. So in this lecture, we will try to quantify about the quantization error, and we'll try to evaluate the signal to quantization noise ratio that is happening in pulse code modulation. So as we had already mentioned that we are not passing the exact signal, we are actually passing the approximate signal of the sample value. Then we are basically incorporating or introducing an error. So in the last lecture, we have also discussed that the quantization error for uniform quantizer would have been given as x of NTS minus xq of NTS. Quantization error is being denoted by the symbol epsilon, and it is the difference between our sampled value of the signal, that is x of NTS, minus the quantized version of our signal. This is what we have already discussed in our last lecture. So here we are assuming that the input signal x of NTS to the uniform quantizer has continuous amplitude in the range of minus x max to x max as shown in the next figure. So what I wanted to say is that our input signal xt is like this one. It is varying between plus x max and this minus x max. Means the maximum value of our input signal is plus x max, and this is the minimum value of signal, which has been denoted by as minus x max. So this is basically our signal, continuous time signal xt, and the excursion of xt is lying between plus x max and minus x max. So basically in this particular figure, we will try to describe the complete quantization process so that we could get review of our quantization process and we get some better insight about the quantization error. So in quantization, what we are doing is we are actually passing our continuous time signal xt to a sampler which will going to sample out or produce the sample of our input signal, likewise this one. So these are basically the samples of our message signal xt. Then what we are going to do that after sampling, we will going to divide our amplitude levels into L number of levels, and the difference between two consecutive levels would have been given as delta or step size delta. These are the amplitude levels. In this example, we have divided our complete amplitude levels into 8 levels, which has been denoted by as minus 4 delta, minus 3 delta up to plus 4 delta. So minimum level is minus 4 delta and the maximum level is plus 4 delta. Then we will going to define the zones, such as the difference between two consecutive levels would have been called as our zones. So basically we have divided our signal into 8 levels. So we are starting with 0, so we're going to have 7 number of zones, 0 to 7. Since our sample value would have been lying in any of the zones, so we need to approximate these signals to a finite amplitude levels. This process is actually being called as our quantization process. So in order to approximate our signal, we are basically pointing the half value of two levels. So if we consider this minus 7 by 2 delta, what I'm trying to say is this minus 7 by 2 delta is lying between minus 4 delta to minus 3 delta. So during this zone, whatever be the value of signal, I mean whether we are talking about this sample or this sample, we will going to approximate that sample value with minus 7 by 2 delta, and this process will going to continue. So whatever be the value of our current sample value, depending upon in whichever zone it is lying, we will try to approximate that input signal or input sample signal with our approximated quantized version of our signal. So obviously during this process we are imparting an inherent error, which is the difference between the sampled value of the signal and the approximated or quantized value of the signal. So this error is actually being called as our quantization error or quantization noise. So from the figure, it is clear that the total variation of the input signal is mapped into L number of levels, as we had already mentioned, such that for plus 4 delta, I mean if the input signal is plus 4 delta, we are approximating it as 7 plus 7 by 2 delta, and if the input signal strength is minus 4 delta, then we are approximating them with minus 7 by 2 delta. So this figure is actually showing two extremities, that is maximum value. For the maximum value, uh, the approximated signal value is plus 7 by 2 delta, and for minimum value or for minimum input value, that is equal to minus 4 delta, we are approximating that with minus 7 by 2 delta. Obviously for different values of input, we'll be having different approximated output signal or quantized value of output signal. This is just for notional purpose for two extreme values of our input signal. What will be the input signal and what will be the approximated signal. So now we will try to evaluate the quantization noise or quantization error. So the total amplitude will lying between x max and minus x max. So the total excursion in the input signal would have been calculated as x max minus times of minus x max. If we are assuming that our signal is symmetrical about the x-axis, then we could say that the total amplitude variation will be equal to twice of x max. So now this total amplitude range is dividing into L number of levels, so that the step size of the input signal would have been calculated as total signal variation divided by total number of levels. That turns out to be twice of x max divided by L, where L is the total number of levels in which we have divided our amplitude values. So now if the signal xt is normalized, then we have, so before we talk any further, let us discuss what do we mean by normalized signals. So if you're talking about any normalized signal, what we wanted that the complete amplitude variation in our signal would lie between 0 to 1. So in order to normalize our signal, what we actually do is we divide our signal with the maximum value of that particular signal, so that the complete variation in our input signal will lie between 0 and 1. Basically, it would be more appropriate if we could say that the modulus value of normalized signal will lie between 0 and 1. So now if the input signal xt is normalized, then we basically have to put x max is equal to 1 and minus x max will be equal to minus 1. So we are doing nothing but we are actually dividing the complete signal with x max for positive value of our signal and minus x max for negative value of the signal, so that the amplitude variation will lie between 0 and 1. So hence the step size would have been calculated as 2 upon L, as x max will be equal to 1. So if the step size delta is assumed to be very small, then the quantization error epsilon is considered as uniformly distributed random variable. Although one should have the idea about random variable, but at this particular moment, if you don't know, just consider it a variable whose value will be random. In short, if I would have to describe the random variable, then we could say that if we need to model any experiment or process, then the outcome of that process will not always be a real number. So if we want to make the mathematical model of that process, then obviously we must have to convert the outcome of those experiments or process to the set of real number. So the mapping or the function by which we actually convert the non-real number set of outcome to the real number set of outcome would have been called as a random variable. And the random variable would have been characterized by CDFs and PDFs. So I'm not going into the greater detail. As of now, I'm just saying that if you have some idea about the random variable, that's good. But if you don't, then just consider it as a variable whose value is random. So while discussing the uniform quantizer characteristics, we evaluated that the maximum quantization error would have been given as, we had already established that relationship in our last lecture, that epsilon max, that is maximum value of quantization error, will be equal to mod of delta by 2. That is, maximum quantization error would have been lying between minus delta by 2 to plus delta by 2. So hence over the interval between minus delta by 2 to delta by 2, the quantization error may be assumed as uniformly distributed random variable. So let me try to give you the essence of uniformly distributed random variable over here. What we have discussed is the maximum value of our quantization error will be equal to plus minus delta by 2. The quantization error is bounded by delta by 2. Its value will not going to be greater than delta by 2. But it could take any value between minus delta by 2 to plus delta by 2 randomly. So its value is not fixed, but it is lying in the range of minus delta by 2 to plus delta by 2, and it could take any value randomly. That is why we are calling random variable. Since the value of delta by 2 is very small, so we could say that this error is uniformly distributed over a complete input signal. So this particular figure shows the uniform distribution function. What it basically describes is the random variable x is uniformly distributed over the range of a and b. Before a, its PDF value will be 0, and after b, its PDF value will also be equal to 0. And in between a and b, it would have been defined as 1 over b minus a. It has been defined as such that the area under the curve, this rectangle, the area under the curve will be equal to unity. So this value would have been evaluated as 1 over b minus a. So this is a standard uniform distribution function. So in the similar manner, if we try to define our uniformly distributed quantization error in between minus delta by 2 to delta by 2, the value of a turns out to be minus delta by 2, and b, for b we have written plus delta by 2, and it is uniformly distributed, and the strength or amplitude of this particular point would have been calculated as 1 over b minus a, that is 1 over delta by 2 minus times of minus delta by 2. So the output turns out to be 1 over delta. So this is the uniform distribution function for the quantization error. So this is basically showing the PDF of our uniformly distributed function for quantization error. So here this is the figure 1. This shows the uniformly distributed random variable x over the interval a comma b, as we had already discussed, and its PDF would have been given as. So the mathematical definition of the PDF of random variable capital X would have been defined as equal to 0 for x is less than or equal to a, and if it is in between, if the value of x is lying between a and b, its PDF would have been given as 1 over b minus a, and for x is greater than b, then its value is also equal to 0. So this is quite clear with this particular figure. Before a, its value is 0, after b, its value is also equal to 0, and in between a and b, its value is 1 over b minus a. So this is the PDF of standard UDF function. So in the similar fashion, we could also calculate the PDF of random variable f of epsilon would be given as that is equal to 0 for epsilon is less than or equal to minus delta by 2, and it is also equal to 0 for epsilon is greater than plus delta by 2, and in between minus delta by 2 and delta by 2 it would have been given as 1 over delta, which would have been described by this particular figure. So this is the PDF for uniform distribution function for quantization error. So it can also be observed from the figure that the mean value of the quantization error is 0. Why we are saying that the area of this left side will be negative and the area of this side will be positive. Both these areas are equal and they are of opposite signs. So when we're going to add them, then we'll get the 0 outcome. So its mean value or average value will be equal to 0. So now the signal to quantization noise ratio of any quantizer would have been defined as signal power to the noise power. I mean, if we are talking about the normalized signal to noise power, then obviously the normalized signal power is the ratio of normalized signal power and the ratio of normalized noise power. So we just need to calculate this normalized signal power and normalized noise power. So we can calculate the normalized signal to noise ratio. So if the input signal xt is known, then the signal power can be calculated. Obviously, if the mathematical description of the input signal xt is given to us, then we can calculate the signal power by calculating its mean square value. So the noise power can be given as, so noise power will be equal to V noise square divided by R, where V noise square is the mean square value of the noise potential and R is the resistance. So here the noise is defined by the random variable and the probability density function, hence the noise power would have been calculated as of now you just can take it as a standard result that the mean square value for any random variable would have been given as the expected value of mean square value of random variable, that is expected value of epsilon square, which would have also been written as bar of epsilon square, which will be equal to V noise square, which is nothing but the mean square value of our noise signal. So the mean square value of any random variable capital X can be given as bar of x square, that is equal to expected value of x square, or we could say that the mean value of x square will be calculated as integration starting from minus infinity to infinity x square f of x dx, fx of x dx, where this fx of x is the PDF of the random variable. So similarly, the mean square value of the quantization error can also be calculated as bar of epsilon square will be equal to expected value of epsilon square, that is equal to integration start from minus infinity to infinity epsilon square f of epsilon d epsilon. So we have already described the value of f of epsilon or the PDF of random variable. So now putting the value of PDF of random variable and evaluating its integration, we are left with integration starts from minus delta by 2 to plus delta by 2. Since our random variable would have been defined in the range of minus delta by 2 to plus delta by 2, and before this and after that its value is 0. So we are left with epsilon square into the PDF value of epsilon will be equal to 1 over delta into d epsilon. So we are left with this in the range of plus delta by 2 to minus delta by 2. So now putting the value of upper limit and lower limit, we are left with this 1 over 3 times of delta cube by 8 minus times of delta cube upon 8. So the final outcome would have been evaluated as delta square upon 12. This is the mean square value of random variable epsilon, or we could say that this is the mean square value of quantization noise. So now the mean square value of noise voltage would have been given as V noise square, that is equal to delta square upon 12. This is what we have evaluated. So now the noise power, or we could say that the normalized noise power would have been given as V noise square upon R, and we could actually calculate the normalized noise power by putting the value of R will be equal to 1. So the normalized noise power would have been given as V noise square, that is equal to delta square upon 12. This is the finalized expression of our normalized noise power in terms of step size delta. So this is actually what I have described. This is the expression for quantization noise power or the quantization error. Keep in mind that this is our normalized noise power. So now we'll try to evaluate the signal to quantization noise ratio in linear quantization. Please keep in mind that SNR is signal to noise ratio, and this subscript Q we have used for describing the term quantization. I mean the noise power that is producing due to the quantization process only. That is why we are calling it signal to noise ratio, and that noise is producing due to the quantization. So that Q describes that. So in PCM system, the signal to quantization noise ratio would have been given as signal power to the noise power. Obviously, if you are talking about normalized value of signal to noise ratio, then we'll be having normalized signal power to the ratio of normalized noise power. So let us say this is our main equation or equation number 1. So normalized noise power would have been calculated as delta square upon 12. In the last slide, we have already described the final expression of normalized noise power. So hence the signal to quantization noise ratio would have been given as normalized signal power to delta square by 12, as this is our calculated normalized noise power. So the number of bits required to encode a sample n and the quantization level L are related as L is equal to 2 to the power n, where n is the total number of bits that has been used to encode a single sample value. So this relationship we have already studied while we are discussing the quantization. So now let us assume that the input X of NTS to be uniform quantizer has continuous amplitude in the ranges of minus X max to plus X max. This is our assumption that our signal is lying between minus X max to plus X max, or the total excursion in our input signal is in between plus X max to minus X max. So therefore the amplitude ranges will be equal to maximum excursion, that is plus X max, minus times of minus X max. Obviously we are assuming that our input signal xt is symmetrical about the x-axis. So the total amplitude ranges turns out to be twice of X max. So hence the step size will be calculated as total amplitude variation divided by total number of levels in which we have divided our amplitude level. So that turns out to be 2x max upon L. So now putting the value of L in terms of n, we have already discussed the relationship between L and n in our previous slide. So we just need to put the value of L in terms of n. So what we have is, so step size delta will be equal to twice of X max divided by 2 to the power n, where n is nothing but it is the number of bits that has been required to encode an individual sample value. So now putting the value of step size in equation 1, we have, please recall, signal to noise power is the ratio of normalized signal power to the normalized noise power. So we just put the value of delta in terms of X max. So what we are left with is 2 of X max upon 2 to the power n whole square divided by 12. So this is the expression for signal to noise ratio. Let us assume that the normalized signal power would have been denoted by P. So the signal to noise ratio would have been evaluated as P, since it is the normalized signal power, divided by 4x square max upon 2 to the power 2n. So here we just squared the two terms and multiplied with 1 by 12. So the final outcome turns out to be 3p into 2 to the power 2n divided by x max square. So hence signal to quantization noise ratio will be given by S by n is equal to 3p into 2 to the power 2n divided by x square max. So this is the finalized expression for our signal to quantization noise ratio. Here one point I want to make it clear that on close observation we could say that the signal to noise ratio is having some exponential relationship with this n. So we can easily say that if the value of n will going to increase, the signal to noise ratio will get increased exponentially. So this is the point that I wanted to make, that this expression shows that signal to quantization noise power ratio increases exponentially by increasing the bits per sample. But here one point is rather important. If we're going to increase the number of bits to encode per sample, the data rate will also going to get increased, and so as the bandwidth requirement. So obviously we wanted high SNR at the receiving side, but there are the constraints imposed by the bandwidth. So now if the input signal and the output signal is normalized, then we have the normalized signal to noise ratio will be given as, or that will be less than or equal to 3 times of 2 to the power 2n. So obviously here we are putting p is less than or equal to 1 and x max is equal to 1, since we are talking about the normalized signal to quantization noise ratio. So this expression would have also been expressed in terms of decibels. So we have signal to noise ratio in dB will be equal to 10 log base 10 signal to noise ratio, that will be less than or equal to 10 times of log base 10 3 into 2 to the power 2n. So basically we have taken the log of this particular expression. On simplifying, what we're going to have is signal to noise ratio in dB will be less than or equal to 4.8 plus 6n. Here we are assuming that the value of log 2 is equal to 0.3. So on simplification, we'll get this final expression that the signal to noise ratio expressed in decibel will always be less than or equal to 4.8 plus 6n, where n is the number of bits required to encode the sample. So this is the final expression. These are the references that we have made for preparing these slides. Thank you very much for your patient hearing.